one type of problem that I asked, and for small numbers, you might think that these might be sort of interesting things to do with high school students, middle school students, whatever. But you have to be a little bit careful for a certain type of problem, and here's what I mean. Suppose you took 24 factorial. So in 24 factorial, what's the exponent of 5? Right, 4, because 24 divided by 5 is 4 plus something, and 4 doesn't give you any more. Again, you don't need to compute too hard, because someone might say, look, okay, when you multiply these numbers, inside of those numbers are 5, 10, 15, 20. Those are the only multiples of 5. None of them are multiples of 25. So if you multiply this out, you get 4 zeros. If you do 26 factorial, how many 5s are in the prime factorization? 6. Again, in fact, I didn't even have to do 26 factorial. I'm going to go to 25 factorial. But the answer is still, as you said, 6. Again, you could just say, two ways to look at it. The only difference from this to this is you multiply by 5 squared, right? So you've added 2 more. Or with the procedure we had, you take 25, divide by 5, you get an answer of 5. But then you take 5 and divide by 5 and get an answer of 1. 5 plus 1 is 6. Okay. Now, if you were just making up sort of a fun exercise for class, you might say, tell me the smallest number that when you take the factorial, you get exactly 5 zeros at the end. And the problem is, there is none. Because 24 factorial has 4 zeros at the end, but to go from here to here, you're multiplying by 5 squared, it jumps up by 2. So there is no number where the factorial has exactly 5 zeros at the end. So, if you're assigning a problem like this to a class, say, give me the smallest number so that the factorial has exactly 5 zeros at the end, there is none. Because remember, it's not like they stay and then they jump up by 1, and then they stay and then they jump up by 1, and they stay and they jump up by 1. Sometimes they jump up by 2. And it's like if you went from 124 factorial to 125 factorial, the exponent of 5 is going to jump up by 3, because 125 is 5 cubed. So if you're giving an exercise like this, you have to do some trial and error. But you have to be careful. If you just ask the problem without doing any computations, there may not be one. So, any other questions on these sorts? Yes?
So this is kind of what we're talking about on number 13, where we're asked to find n such that the exact value of n factorial has exactly 1,000 zeros. So I kind of get where you would start with by what your exponent of 5 is, but then what do you do?
Okay, so I don't know if the book says you may need to do some trial and error, but so what you want is, if you want exactly 1,000 zeros, that means you want the exponent of 5 to be 1,000. Well, the way the exponent of 5 comes from in these things is you take the number that you're doing the factorial for and you divide by 5 and you keep that procedure. Well, there's a certain number that if you divide by 5, you're already at 1,000. Namely, if you started at 5,000, then the exponent of 5 is going to be a lot bigger than 1,000, right? Because you take 5,000 divided by 5, you already have 1,000 multiples of 5, but then when you add in the multiples of 25 and 5 cubed and so on, that's going to be much bigger than 1,000. And again, you have to do trial and error for this. So 5,000 is significantly too big. How much would you like to drop it by? 3,000 to 3,000 to 4,000, or pick something you'd like to try. Because the only way we're going to get this is by a guess and check. So 5,000 5,000 is much too big, so do you want to drop down to 4,000 or 3,000 or 4,000? So if we try 4,000, for the exponent of 5, 4,000 divided by 5 is 800. 800 divided by 5 is 160. Well, that's pretty good because these add up to 960, and if we keep going, we're probably not going to be too much bigger, so we're at least in the ballpark. 160 divided by 5 is 32. 32 divided by 5 is 6. And 6 divided by 5 is 1. So we multiply all the numbers from 1 to 4,000. 800 are multiples of 5. Of those, 160 are multiples of 5 squared. Of those, 32 are multiples of 5 cubed. Of those, 6 are multiples of 5 to the 4th. Of those, 1 are multiples of 5 to the 5th. So the total number of powers of 5 I have, if I add up all those numbers, I get how much? 999. Missed by that much. Okay. So what we need is, we need exactly one more power of 5. So we can say, okay, after 4,000 factorial, the next one is 4,001 factorial, which you get from multiplying by 4,001. But if you don't multiply by a multiple of 5, the exponent of 5 isn't going to change, right? So 4,001 is a bigger number, but that doesn't change. Same way, if you started with 4,001, you'll get 800 plus a remainder. 4,001 isn't going to do the trick. What about 4,002? No, this number is not going to jump up until I reach the very next multiple of 5. Fingers crossed that when I reach the next multiple of 5, I haven't reached a multiple of 25, because in which case I would have jumped all the way up to 1,001 and there wouldn't be an answer. Well, what's the next multiple of 5 after 4,000? 4,005. Well, if we check this for 4,005, you get 801. Well, that's good because that bumped me up by 1, but that's all I want to bump up by. Then if I do 801 divided by 5, I get 160 plus a fraction, or plus, a number. Well, that's plus a fraction. But that's perfectly good because that means at this point, I'm precisely where I was before. So all I've done is, in the 4,005, I've given this one extra multiple of 5, not an extra multiple of 25. So the smallest number that works is 4,005. If you wanted all the numbers that work, it would be 4,005, 4,006, 4,007, 4,008, 4,009, because once you get to 4,010, you've tossed in another one. So there are precisely 5 numbers that their factorial has exactly 1,000 zeros at the end, but the smallest one is 4,005. And I know in most classes you're usually used to, take the algorithm and turn the crank, and you're not used to sort of guess and check. The only way to do this is really to guess and check. I mean, you can start off with some logical guesses. That is, if you want 1,000 zeros, you're obviously not going to go any higher than 5 times 1,000. And then just sort of make a rough guess as to, well, if this was really much, much, much too big, then I want to shrink down a whole lot to maybe 2,000 factorial. If this wasn't all that much bigger, maybe try 4,000 factorial. But the point is, kind of like with Goldilocks, some of your guesses might be too small, some of your guesses might be too big. You're looking for a guess that's just right. And as we saw, if the problem was not well formulated, there might not be an answer that's just right. But hopefully, whoever has made up the question has checked it first. Unless they cover their base and say, okay, give me the smallest number if it exists with this property. If one doesn't exist, explain why. That sort of covers your behind if you're asking a question. question.
Number 17. Didn't quite get the.
From the same group? Okay. Okay, so we're looking at A, 2 times 30 times 5 times 7 plus 11. B is 2 times 3 times 5 plus 7 times 11. And C is 3 times 5 times 11 plus 2 times 7. Without actually computing these things, explain why none of these is divisible by a prime less than 13. Another way of saying not divisible by a prime less than 13 is show why none of these numbers is divisible by 2, 3, 5, 7, or 11. Well, as with many problems, once you see the idea, you can turn the crank. So here's the idea. Suppose you have A plus B. And suppose A is a multiple of 7 and B isn't. If A is a multiple of 7 and B isn't, what can you say about the sum? Is it a multiple of 7? No. So the things that you know are, if A and B are both multiples of 7, then so is the sum, right? Because if you can factor 7 out of A and 7 out of B, you can factor 7 out of the sum. If neither A nor B were multiples of 7, can you say about A and B individually? If neither one is a multiple of 7, can the sum possibly be a multiple of 7? Yes, because again, 1 plus 6, 2 plus 5, 3 plus 4. In other words, the amount that the first one misses by being a multiple of 7, the second one might sort of compensate for it. But if one is a multiple, and since addition is commutative, it doesn't matter whether I'm talking about A or B. If one of them is a multiple of 7, and the other one is not, what about the sum? It cannot be. For this reason, suppose, again, there's lots of ways I could write this. Suppose this is a multiple of 7. Suppose this is not a multiple of 7. And let's take a look at the answer. B is C minus A. If C was a multiple of 7 and A was a multiple of 7, then C minus A would be a multiple of 7. In other words, if this was, so sort of proof by contradiction, if C was a multiple of 7, that would force B to be a multiple of 7. So, the moral of the story is, if you add two numbers, if one of them is a multiple of 7 and the other one isn't, then the sum isn't. This might have been a common theme that you might have had in discrete math, that is sometimes you're adding numbers. If one has the property and the other one doesn't, then the sum doesn't. It probably came across as like being irrational. If you take a number that is rational plus a number that is not rational, then the answer is not. Did you sort of do things like that in 660? Okay, so this is sort of the same thing. Well, there's really nothing special about the number 7. I mean, I just picked it for simplicity. If you added two numbers, if one is a multiple of 11 and the other one is not, then the sum is not. And in fact, I picked two primes, 7 and 11, but I mean, I don't have to pick primes. If you add two numbers, if one is a multiple of 20 and the other one is not, then the sum is not. Well, if you look at all of these numbers, if you look at 2, 3, 5, 7, 11, in little a, no matter which of these primes you pick, one of these is a multiple of that number, and the other one isn't. Like, if you pick 2, this is a multiple of 2, this isn't. If you pick 7, this is a multiple of 2, this isn't. If you pick 11, this is a multiple of 11, this one isn't. So, what I basically did is, I took five prime numbers and just sort of split them into 2 groups, and if I split them into 2 groups, in each case, any of the prime you pick, if you pick 2, 3, or 5, this is a multiple and this isn't. If you pick 7 or 11, this is a multiple and this isn't. Here, if I take 3, 5, or 11, this one is a multiple and this isn't. If I take 2 or 7, this one is a multiple and this isn't. So in each case, it's the same idea. You're adding up 2 numbers, one of which is a multiple of something. The second one is not, therefore the sum is not. So as with many things, once you sort of see the tool that you use, things become significantly easier.
Is it the same, or is it sufficient to say sum of 2 relatively prime numbers is always prime? Does that give enough reason to that?
Well, the sum of 2, well, if we go back to the thing about, if you take 2 numbers which are not multiples of 7, their sum could be.
Okay.
In the same way, like if you take 2 odd numbers that are relatively prime, if you add them up, well, okay, I might be okay. Okay, so your question is, if you add up 2 relatively prime numbers, do you get it prime?
Yeah.
Okay, so certainly if you add 2 odd primes, you're going to get an even number that's not prime. As you will see, and as you might have seen, in mathematics there are a lot of things where if you just say the words over a few times, it certainly seems plausible. And I've done this many times in my own research. You look at various things that are known and you go, oh, well, then so-and-so should be known, and then you sort of think about it and you can't really prove it, and then you ask somebody else, and they said, yeah, but here's an example. I go, oops. So sometimes I get too anxious to look for the proof, not realizing there's a balance. Sometimes I should look for the proof, but sometimes I should look for an example of the other direction. Other questions? Yes.
For sections 3.4 and 3.5, I was sort of a little bit confused about the first 8 problems, but maybe if we look at 3 or 8 in particular.
Okay. Okay, so you were wondering about 3 and, was 3 the one the first one was you were
Either
wondering?
3 or 8. I don't know if we have to do both, but
So let's go with 3. So we've got A, B, and N are positive integers. We want the greatest common divisor of N times A and N times B equals N times So there are various approaches that we could take. So let's just sort of play, because again, some of these things you have to experiment with. So suppose C is the greatest divisor of A and B. So that means A is a multiple of C, and B is a multiple of C. But then I'm wondering about n times A and n times B. But notice, if I multiply this by little n, I didn't have to put the n there, but so in fact I'll write this a little bit differently. If I multiply both of these by n, this is n m times c, this is little n big N times c. So here's what I've noticed. And again, as I look at this, I keep moving the little n around on the right-hand side. It really doesn't matter. What this is saying is, if you're a common divisor of A and B, then n times C is a divisor of n times A, and n times C is a divisor of n times B. So if C is the greatest common divisor of A and B, that means NC is a common divisor of NA and NB. So if C goes into both A and B, then N times C goes into both N times A and N times B. Well, that means this side is a common divisor of NA and NB, but this is the greatest common divisor. So what we've actually shown is the greatest common divisor of NA and NB is greater than or equal to N times the greatest common divisor of A and B. So that's one direction. Because this is a common divisor of NA and NB, therefore it's less than or equal to the greatest common divisor. So in other words, what I'm doing is I'm sort of playing around with these things, because you don't instantaneously come up with a proof. You sort of play around with these things and say, okay, by playing around with these things, what have I actually proven? So by playing around with these things, I can see that the greatest common divisor of NA and NB is greater than or equal to n times the greatest common divisor of A and B. Now, let's see what other things I can come up with. If C, and again, I'm not coming up with a proof, I'm just sort of playing. Because I'll play with these things, and then I'll see what I come up with. Another fact about the greatest common divisor of A and B is it's the smallest thing that can be written as a multiple of A plus a multiple of B, right? So C can be written as, say, a multiple of A plus a multiple of B. Using the fact that the greatest common divisor of A and B is the smallest number that can be written as a multiple of A plus a multiple of B. Again, I'm just playing. I don't know where this is going to take me. But again, multiplying by n, because the only thing I know about the relationship between NA versus A and NB versus B is I get from A and B to NA and NB by multiplying by n. So again, I take facts about A and B and multiply by n and see what it tells me. So if I multiply both sides here by n, this says that I can write, remember, C is just a shorthand for the greatest common divisor of A and B. This says I just wrote n times C as a multiple of NA plus a multiple of NB. So far, so good. But what did we prove about greatest common divisors? The greatest common divisor is the smallest thing, smallest positive integer, the smallest positive integer that you can write as a multiple of NA plus a multiple of NB. Again, this is the smallest thing that you can write as a multiple of NA plus NB. Well, notice NC is a multiple of NA and NB. Well, if this is the smallest thing that can be written this way, and NC can be written this way, then this can't be bigger than NC, right? So this is less than or equal to NC. Now, let me confess. I sort of played with what it meant to be a greatest common divisor, accumulated facts, and looked and noticed that these facts actually gave me a proof. This is not exactly chock full of intuition. But the point is, what we do is, we look at the definitions of things and we see what properties they have. So the first thing, again, we noticed was, if you take a common divisor of A and B, and you multiply it by n, it's a common divisor of NA and NB. So it has to be, since this is a common divisor of NA and NB, it has to be less than or equal to the greatest common divisor. That's half of it. The other half is sort of the new way of looking at things, which you probably didn't see much until this course, that another way to look at the greatest common divisor is not as the greatest thing with a certain property, but as the smallest thing with a certain property. The smallest thing that can be written as a multiple of A plus a multiple of B. That says n times it can be written as a multiple of A plus a multiple of B. But this is the smallest thing that you can write as a multiple of these two. Well, if this is the smallest thing that you can write as a multiple of these two, and you can write this as a multiple of these two, then this has to be less than or equal to NC. So I just sort of collected facts and noticed, oh, these facts gave me the information that I wanted. So my apologies, this is not exactly chock full of intuition. You could probably do this by looking at the prime factorization of A and looking at the prime factorization of B and so on. But in terms of just using the basic properties of greatest common divisors, here's one argument. And my apologies if it's not exactly chock full of intuition, but I'm just sort of collecting facts about greatest common divisors. And it's kind of like you're doing a jigsaw puzzle. I'm looking at all the different pieces of accumulating facts that I know, and then I just see, well, do any of these facts fit together? Or how do they fit together? And they actually fit together to tell me what I wanted. So, not exactly chock full of intuition. Okay. To go in the opposite direction of what I just said, for number 8, it might actually be easier to look at things in terms of the prime factorization. So, at least if I'm thinking about it. So is problem 8 saying you're comparing the greatest common divisor of A and B to the greatest common divisor of A to the n and B to the n? Well, to me that sort of asks about greatest common divisors because suppose you take a given prime t. Then what is the exponent? I could write more, but I'll try to keep it limited. What is the exponent of p in the greatest common divisor of A and B? Well, you look at the exponent of p in the prime factorization of A. You look at the exponent of p in the prime factorization of B, and which one do you take, the bigger one or the smaller one? If you take the greatest common divisor of A and B and you focus on a particular prime P, are you taking the bigger exponent or the smaller exponent? The smaller. The bigger one is the least common multiple. So, in other words, A looks like, say, P to the S times other primes. is p to the t times other primes. And then the exponent of p, in this case, is the smaller of s and t, right? So if I'm looking at again, and maybe you could do problem 3 this way, doing in terms of prime factorization. I want you to see multiple ways to do it. Doing it in terms of prime factorization might not be the shortest way, but it might be more intuitive. So if I'm looking at the greatest common divisor of A and B, for any prime P, A is P to the S times other stuff, B is P to the T times other stuff, and the exponent of prime of the exponent of P in the greatest common divisor is the smaller of these two exponents. Well, if I raise A and B to the nth power, all the exponents here if you take something and raise it to the nth power, all the exponents in the factorization get multiplied by n. So this becomes P n s times the other primes. Again, their exponents change, but I don't care. This becomes P to the nt times other primes. So now let's look at this. If you take the greatest common divisor of A and B, the exponent of P is the smaller of S and T. If you raise that to the nth power, that's your C was the greatest common divisor. So the exponent of P would be the smaller of these. When you look at C to the n, you would just be taking n times the smaller of these, right? So the exponent of P in here is n times the smaller of these two. Because again, the exponent of P in here is the smaller of S and T. Then when I raise it to the nth power, it's n times the smaller of S and T. But if I compute the greatest common divisor of A to the n and B to the n, I'm taking the smaller of those two exponents. Well, if S is the smaller one compared to T, then NS is smaller than NT, right? And if T was the smaller one, then NT is smaller than NS. In other words, when you compare NS and NT, that's going to be n times whichever was the smaller one of S and T. So, the exponent of P in here is the smaller of these two exponents, and the smaller of these two exponents is precisely n times the smaller of n and t. The moral of the story is, if you take the greatest common divisor of A and B and raise it to the nth power, and you compute the greatest common divisor of A to the n and P to the n, for any prime you pick, it has the same exponent in here. Well, if these two numbers have the same exact prime factorization, well, that's what we just proved. No matter what prime you pick, it appears to the same power in both of these. Since these two numbers have the same prime factorization, they have to be the same. So I can understand why some of those early problems in that section were troublesome, because they're a bit more on the theoretical side. But for this one, you can kind of fall back on the prime factorization.